I'm Alan Fenn at MIT Lincoln Laboratory, and this is lecture number 11, Displaced Phase Center Antenna Measurements Using Planar Near-Field Scanning. This lecture is part of the lecture series Adaptive Antennas and Phased Arrays. Here's the course content breakdown by topic. This is lecture number 11. We'll be covering some adaptive antenna theory in the context of radar clutter suppression. We'll be covering some phased array theory, antenna measurement techniques. We'll be including the effects of array mutual coupling, and we'll be investigating far field and near field characteristics. Chapter 11 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, can be used to supplement this lecture. So the purpose of this lecture is to review the displaced phase center antenna radar clutter cancellation technique and to describe a near-field measurement technique to quantify the clutter cancellation performance. Here's an outline of the talk. After a brief introduction and background, I'll describe the methods and materials, some results, and then summarize. So by way of introduction, adaptive antenna systems have been explored extensively by numerous researchers since the 1950s. And the primary functions of an adaptive antenna system are to minimize or null interference and jamming, to suppress radar clutter, and to detect radar targets. So in this lecture we're going to concentrate on adaptive array clutter cancellation. Now in lecture 2 we described a DPCA radar clutter cancellation technique for radar target detection. So consider the diagram shown here. We have a moving DPCA platform, we have a moving target over the Earth's surface, and we have fixed clutter. So there are two displaced phase centers, A and B, and what we would do is transmit from the full aperture at points A and B corresponding to the radar pulse repetition interval, or the PRI. We would then receive at displaced phase centers A and B such that there's an equivalent monostatic radar location denoted as AB. In other words, we transmit here, we receive on B and A here, such that there's an equivalent monostatic radar location at the midpoint. So in this case, stationary background clutter can be canceled and a moving target can be detected due to its phase shift that occurs in 1 PRI. Now to implement the DPCA technique, we need a corporate feed with 2 or more receive phase centers. So in the diagram shown here, we've got 2 phase centers denoted A and B. So there's a wave front impinging on the array. There are N array elements shown here, and we would allow mutual coupling to exist between the array elements. In lecture 2, we showed that mutual coupling had a large effect on the DPCA performance. Now after the signals received in each of these antennas, we split the signal 2 ways to the 2 phase centers. And there's a set of TR modules in phase center A and a set of TR modules in phase center B. These TR modules are used to put a phase weighting on to steer the beam in a desired direction, and an amplitude taper to create low side lobes. So we have a summed array output A and a summed array output B corresponding to the 2 phase centers. So in this lecture, TR module errors are included, as well as array mutual coupling, in the DPCA measurements. Here's an example of overlapped and split receive apertures. So the amplitude taper is generated by the array TR modules, and that's used to move the phase centers with respect to one another. So here we show a cosine type amplitude illumination for phase centers A and B, and they're separated by the distance delta, or the phase center separation. And basically what that means is the center of gravity, or the midpoint of these cosine distributions, sets the phase center displacement. And this is the direction of motion. So this is a case of overlap receive apertures. On the right we show the case of split receive apertures where they're fully split apart. Now due to array mutual coupling and asymmetry, the DPCA performance can be degraded. And what we're showing here is that if we have a large array and here's the direction of motion to the right. If we form a main beam on subarray A on the right, there's a large number of passively terminated elements on the left. If we form a beam from phase center B, then there are a large number of terminated elements on the right. So the array termination affects the phase center radiation patterns and the match between the patterns of phase centers A and B. And typically we would use guard bands surrounding the subarrays to restore symmetry of the two phase centers. Now, to compute the DPCA performance, we need to calculate the pattern correlation matrix, as shown here for the case of two DPCA radiation patterns. So we're forming the pattern correlation matrix, which consists of the correlation between two channels, as shown here. There's a transmit pattern, magnitude squared, and then multiplied by the receive patterns of the ith and jth channels, or two channels. And there's a phase factor, which takes into account the phase center separations. There's an amplitude weighting function that would depend on the radar waveform, but in this lecture we assume that A is just equal to 1, so that the clutter cancellation depends only on the radiation patterns alone. And we're integrating this quantity over the observation angles theta and phi in spherical coordinates. So again, working with the pattern correlation matrix that we just showed in the prior slide, the output signal-to-noise ratio of this two-channel DPCA adaptive nulling system is inversely proportional to the quantity shown here. C equals 1 minus magnitude of M12 squared divided by M11 M22. So this factor plays a role in the clutter cancellation factor, reducing the clutter power received by the radar system. And in this lecture, the cancellation shown above is expressed as a positive dB value by taking 10 log base 10 of 1 over C. Let's now describe the methods and materials. So in this lecture, we're going to use a near-field scanning measurement system to collect the DPCA radiation pattern information. And we use a planar near-field scanner. There are other types of scanners, such as planar polar, cylindrical, and spherical. And I'll show why we're using the planar in the following slides. Now typically we want to know the far field performance of a DPCA array, and we can get that from near field measurements in the following manner. So if we wanted to get a far field measurement of the radiation pattern of the DPCA array, what we would need to do is take this large aperture and move each phase center to the center of rotation, and then rotate the antenna and collect the far field pattern at a large range distance, typically 2d squared over lambda. Now for large apertures, this translation can be difficult. The reason we want to translate the phase centers onto the center of rotation is to keep the multipath the same. This measurement may be done outdoors where there could be significant multipath. What we'd like to do is characterize the DPCA phased array in a large anechoic chamber. So to do that, we place a near-field probe close to the antenna, a few wavelengths away, scan the probe, measure the amplitude and phase, and then use a mathematical transform to calculate the far-field radiation pattern. Now the mathematical transformation to do this is described in Lecture 12. So this slide shows the DPCA near-field measurement concept. As shown here, we have a large rectangular aperture with two phase centers that are overlapping. We have phase centers A and B, separated by the distance P. And with the planar near-field scanning technique, all we need to do to measure phase center A is to do a probe scan as shown here, and then do a separate probe scan for phase center B, where the probe scan is displaced by P, which is the phase center displacement. And so the prototype DPCA phased array antenna that we'll be describing in this lecture has potential application for a space-based radar in low altitude orbit. So here we're showing the Earth, and so here's the space-based radar antenna. It wants to scan a beam out to the horizon. It would not scan a beam directly below the satellite because the high grazing angle would create significant clutter and it would be difficult to see a radar target. So this is a nadir hole or exclusion zone. So we would be scanning the radar beam between the minimum cone and this maximum cone at the horizon. So in the nadir hole, radar clutter is strong and dominates over moving targets. And so scanning is desired at any azimuth angle between the edge of the nadir hole and the horizon. So since we don't need to scan into the nadir hole, a monopole phased array antenna could be used for this application. So this shows a shaped elevation pattern. The monopole antenna would have an omnidirectional azimuthal characteristic. Here's an example monopole array shown here. And the array would consist of quarter wavelength monopole elements over a ground plane. And in Lecture 2 we analyzed a monopole array for the DPCA application. Here's the DPCA test array layout. And so this was a 96 element test array with a 1.46 meter active portion. And the array contained TR modules with two phase centers to move the phase centers apart. The array contained passively terminated elements surrounding the 96 element active portion of the array. And the dots represent the locations of the monopole elements. This shows a photograph of the prototype DPCA test array built at Lincoln Laboratory. So it has 96 elements as part of the DPCA phase centers, and there are two rows of passively terminated elements surrounding the DPCA array. Here's a block diagram of a representative DPCA beamforming network. The actual test array included just phase shifters and variable attenuators to move the phase centers. But in a real radar system, there would be power amplifiers for transmit and low noise amplifiers for receive. But what we do in the test array is we have the monopole receive elements. We go through a two-way power splitter, and then a phase shifter for each phase center and a variable attenuator for each phase center. And so there are two outputs from this array, phase center A and B. In the near field scanning case, if the antenna length is L as shown here, and we scan a probe in the near field distance capital L, then the angles at which the far field radiation pattern would be accurate would be out to approximately the angle formed here, theta max. So we do want to overscan the length of the test antenna. This slide shows the measurement geometry for 1D and 2D near field measurements for the 96 element DPCA array. So in general, the near field sample plane would be two-dimensional, and a grid of near field points would be sampled over a large planar surface. And in this lecture we used a 1D horizontal centerline cut of the near field data to compute the far field radiation performance of each phase center. Here's a block diagram of the near field scanning system. We had a near field probe and a probe positioner with an interferometer to record the location of the probe. The probe was motor driven. Here's the 96 element test array of monopoles, and then we had a receiver to record the data. And the computer calculated the far field radiation patterns from the near field data. And so we were transmitting from the probe and receiving from the 96 element test array with the two phase centers. Here's a photograph showing the displaced phase center antenna under test in the near field facility. So here's the monopole array, here's the probe antenna with absorber surrounding the probe, and here's the probe positioning system. So we would scan the probe across the horizontal center line of this displaced phase center antenna. Let's show some results. Here's the measured one-dimensional near field for the DPCA test array when the main beam is scanned to minus 40 degrees from broadside. On the left is the relative amplitude for the principal polarization and the cross polarization in the near field. So the cross polarization is down typically by about 25 dB or more. And on the right we show the phase, and we see the linear phase slope, which is due to the beam being scanned from broadside at minus 40 degrees. And so these data are being plotted versus column number across the horizontal center line. We can take the near field data shown in the previous slide and compute the far field radiation pattern. And so this is with the main beam steered to -40 degrees. This is for beam A, phase center A, where the phase centers are displaced by 12.7 centimeters. Next we show a comparison of the measured two-way radiation pattern for phase centers A and B. So the pattern shown here is essentially the product of the transmit antenna pattern and phase center A and B receive patterns. And so what we see is very good agreement between the beams A and B for the phase center displacement of 12.7 centimeters. So since the beams are very well matched, we would expect to get good clutter cancellation performance. And that's shown in this slide. So this shows the measured DPCA cancellation as a function of the radiation pattern threshold. So the radiation pattern threshold is being varied from the peak of the main beam all the way down to the low side lobes of the antenna. So the cancellation is plotted up to 60 dB, and we see that as we take the data down toward the side lobes, that the clutter cancellation performance levels off a little below 45 dB. This is at 1.3 gigahertz, where the phase center displacement is 12.7 centimeters. And so the pattern threshold is reached at approximately the -10 dB level. So most of the radar clutter cancellation performance depends on the main beam. This slide shows the measured DPCA clutter cancellation performance versus scan angle for the 96 element test array. So 0 degrees would be broadside looking into the null of the monopole, and we would not expect to get much cancellation in this nadir hole region. And so the desired scan sector is from approximately 30 to 60 degrees. And we see the clutter cancellation is on the order of about 40 dB or better at these larger scan angles. Now we show the measured DPCA clutter cancellation versus frequency. Center frequency is 1.3 gigahertz. And we see that there is an effect of frequency. Clutter cancellation is varying from about 36 dB up to about 46 dB over the band. And so frequency effects have to be taken into account in a DPCA radar system. Now it's possible for TR modules in the receive array to fail, and this slide looks at the measured DPCA cancellation with TR module failures and then compensating for the failures. So by failures and compensation, what we mean is if we have a failed module in either phase center A or B, we would turn off the corresponding module in the other phase center to compensate for the failed module. And that restores the phase center characteristics from one phase center to another. Now this shows an experiment that was conducted where modules had been simulated as being failed, and so the heavy curve is the uncompensated cancellation as the module failures increase to 10%. By compensating for the failed module, in other words, turning off the corresponding module in the other phase center, we see we can restore roughly 40 dB clutter cancellation, and so that's a significant effect. So let's summarize. So in this lecture, planar near-field measurements of displaced phase center antennas have been described in this lecture, and examples of measured DPCA cancellation performance for a monopole array have been given, and it was shown that the DPCA cancellation depends on the pattern threshold, the main beam scan angle, frequency, and TR module failures. Chapter 11 of the book Adaptive Antennas and Phased Arrays for Radar and Communications contains additional information to supplement this lecture.